Hello guys, welcome to the what. So today we will see MATLAB simulations on an inverter, a single phase half bridge inverter, which is the first inverter that we will see, the most simplest one, right? We will trigger the semiconductor switches using a square pulse, right? So let's get started. So what is an inverter? An inverter is a converter. Basically it will convert DC voltage to an AC voltage, right? So how this will work? So this is a diagram of a single phase half bridge inverter using square pulses, right? So total value of the voltage across this is 2 VDC, right? And the voltage across load that we will get would be VAC, right? So what is the value of this VAC? We will see. So now these are the gate pulses with 50% duty cycle. We know that 50% duty cycle means from the total time, 50% of the time it would be 1, and the other 50% of the time it would be 0, right? Now we can use a pulse generator from MATLAB, but we will not use that. We will create our own pulses, right? So we will give this pulses to our first inverter, right? And we will give same pulses but with a NOT gate to our second semiconductor switch, right? So what will happen when in the first 50%, right? So this would be something like this. It will be positive for 50% of the time, and then it will be 0 for 50% of the time. Then it will be positive, then it will be 0 across the first IGBT. The second one will be NOT gate, so it would be opposite. It would be 0, then some value. Here it will be 0, then some value, right? So now in first 50%, we can see that the first gate is positive and the second gate is 0. So second gate is 0. That means the second one is open circuited. First one is short circuited, right? So current will flow from this VDC to this. It will go from this load and it will complete the circuit. So current will be in this direction, right? So if we see the output, then we will get some positive. Let me clear this thing up. So let me draw the gate pulses. So the first one, we have a positive, then 0, then positive, then 0. Now this is the second gate, this one. This is the first gate, this is the second gate. So it would be negative because it is NOT gate to the first one, then positive, then negative, then positive, right? Now let's check the load. So I'll give L for load. So while the first one is on, so positive will be connected towards here, negative will be here, right? And current will flow in this direction. So it is positive. So we will get something like this, right? Now, while the second 50%, what we will get, this VDC will work. So current will flow from here. This will be positive because the gate pulses in the second half is positive for the second gate. So it will be plus here and minus here, and current will be travel from this to this, right? That means current is negative. So it will go negative, it will come here, it will continue, right? So for a DC input, we are getting AC output. And how AC? This would be the zero line, right? So the area of the positive cycle is equal to the area of the negative cycle, right? So this is an AC. The input was DC, right? But this would be VDC. The magnitude of this would be VDC and minus VDC. But total input that we are giving across this whole inverter is actually 2 VDC. So we can say that in a half bridge inverter, we are getting 50% output, right? So 50% output we are getting in a half bridge inverter. So let's see the working. Let's see the simulations. So these are the components that we required: a DC voltage source, RLC series branch, voltage and current measurements, IGBT or MOSFET, but normally in inverter we use IGBT, semiconductor switch, then a sine wave generator, gain block, add block, constant, and a relational operator. So these, we are using these 5 blocks to generate our square wave. Then a logical operator for NOT gate, scope for seeing the waveforms, display for seeing the magnitude, power GUI to work in continuous simulation, one ground, one multiplexer, and one RMS block. Now we will use an RMS block because from now we will work on AC signals, right? So let's start. So let's see what all do we have. So let's take one DC voltage. We'll take this black one, DC voltage source, and we will take RLC. We will take RLC series branch. Then we will take voltage measurements. This one. We will take current measurements, which is this one. Voltage measurement, current measurement, then IGBT. We will take this one, this IGBT. We will take sine wave generator, or we will, let's take a triangular wave, because we can use a sine wave generator as well, but we will see its application later. Right now we will take this triangular wave. So let's take one gain block. Now we'll take add block. Then let's take constant. Relational operator. We'll take logical operator. We'll take scope. We will take display. GUI, then ground, this one, then we will take a multiplexer, take an RMS block. This one, right? So we got everything. So let's make the circuit. Here also there would be two different circuits. One is the main circuit, second is the triggering circuit, right? So let's make the circuit. So DC voltage will be here. Let's take two DC voltages. Now we need to take a load. We need to take two IGBTs. Just open them and untick this measurement port to avoid confusion. Let's connect. Let's take current measurements. Let's invert this format, rotate and flip, format block upside down. So in the first half of the cycle, this would be positive, this would be negative, and the current direction will be this, right? So we will put it here. And we will take a voltage block as well. Here it will be positive, here it will be negative. One diamond block, we will convert this to NOT gate. We will connect it here. Then we will make our triggering circuit. So let's see the output through the scope. On this triangular wave, let's set the frequency to the Indian power frequency, that is 50 Hertz. Phase degree, we will convert it to minus 90 degree. I'll explain you later that why we are doing minus 9. Here gain would be 0.5. Constant that we will add would be 0.5 as well. And this constant would be 0.5 as well. To get 50% duty cycle, right? So let's observe this gate pulses. So why we took this minus 90 in this triangular pulse generator in phase, because we want to start this triangular wave from this point. So we know that when we compare these two, when a triangular wave is smaller than the constant wave, we'll get a positive output. So we want to start our simulation with a positive output. That was the reason that we took this one, right? So now these are the gate pulses. The frequency is 0.02 and the duty cycle is 50%. So that is perfect, right? So now connect this gate pulse here, connect a NOT gate here. Let's take one more scope to see the gate pulses. Okay, let's see everything in one thing only. Let's take this scope and connect it with current. Let's see current in one only, right? So we will observe everything in one gate block only. Let's put this ground here. So the value of voltage, it will be RMS, and the display. Now first input we will get from the constant value of the voltage, that is this and this, right? So one constant value of voltage, that is the first one. Second one would be the first gate. Third one would be the second gate. The fourth one would be the output waveform, and the fifth one would be the current. So 5, right? So let's take 1 and 2 for the gate pulses, input and output, and 1 this. Okay, they are not allowing us. Let's take these only. Or for now, let's not take the input voltage, and let's take only the output in the gate. Now take one more scope. Here we will compare input and output voltages in one screen only. So the first graph will be of the gate pulse. The second graph would be of the NOT gate pulse. Third one would be the voltage. Fourth one would be the current. Here, the first one would be the output voltage. Second one would be the first one would be the input voltage. Second one would be the output voltage. Right. So this will, and the input will be of 50 volts each. So that means total of 100 volts. So what is there? Everything, I guess everything is fine. Let's run the simulation. Okay, we forgot to convert this. This is only an R of 10 ohm. Right. So let's replay this. So here we are getting 49 RMS value, right? So first of all, let's check the input and output voltage. So as we discussed earlier, we will actually get 50% output. So here we can see that 100 is the input, and we are getting 50%, 50 positive and 50 negative. That's the output, right? So RMS will be 50. Let's observe the pulses, right? So in the first one, we can see that for 50% duty cycle, it is positive. Next 50% it is negative. The second one is the exactly opposite. The third one is the output voltage, right? So it is 50 positive, then 0, then minus 50. And the fourth one is the current. So current and phase are exactly same because we are connecting only R load here, right? So no phase difference between those two. So these are the exact pulses that we will get, right? So this was the MATLAB simulation on single phase half bridge. So why half bridge? We have half bridge because the total voltage that we are giving across the whole circuit is 100 and we are getting 50 volts as the output, right? So this was the simulations on half bridge single phase inverter. So if you have any doubt or if you have any concerns, please do let me know in the comment section. I'll be happy. I'll be respond accordingly. And in future, if you want any other converters to be simulated, just let me know, right? Thank you. Bye bye.